rate laws, expression that provides relationship between rate of reaction and concentration of reactants. These are determined experimentally, but never involves the product. It only has the reactants. And we do not use the coefficients of the equation as we did in the previous problem. Why? Because everything is determined experimentally right here. So if we have the following equation, 3a plus 4b plus 2c is going to yield the products. We don't care about the products because it only determines and dependent on the reactants. So the general equation for the rate is equal to K, concentration of A in brackets. Remember, all concentrations must be in brackets, to some power X times concentration of B to some power Y and concentration of C to some power Z, in which substances or the reactants are A, B, and C. The reaction order is X, Y, Z. That is the power or the exponent that we will be solving for. And K is the rate constant. Remember, all of these are only determined experimentally. So usually for problems that involve rate laws, you will be given a table with data with multiple trials. You have given the following reaction and experiment at 25 degrees Celsius. They will give you the equation. In this case, it is A plus B plus C yields D. And again, we don't care about the products, so D does not matter. Even if the products are given to you in the data table, we ignore it. So in this problem, we are going to determine the reaction order of A, B, C, the overall reaction order. We're going to determine the rate constant and its units, and we're going to write the rate law. To solve for the reaction order, what we want to do is set up a ratio. In general, we want the bigger numbers on top, the smaller numbers on the bottom when we do the ratio, because the math is a little bit easier. Second, when we set up the ratio, we want to cancel out as many of the unknowns as possible to make our calculation easier. So the first thing I'm going to do is write a generic rate law for this problem. So rate equals K, which is the rate constant, my reactant A concentration, to some power X, which is the reaction order that we're solving for, times the concentration of B to the Y reaction order, and concentration of C to reaction order Z. Since we don't know if X, Y, and Z are the same or different, we must use different variables. After I write a generic rate equation, I need to set up my ratio. So I'm going to look at my experiment and figure out which reactions will simplify as many variables as possible. So I'm going to solve for A first. To solve for A, I know B and C must be the same concentration for the experiments that I choose. If I look at my table, I see that experiment 1 and experiment 2, the A concentrations are different, but B and C are the same. So I'm going to use experiment 1 and 2. I'm going to put 2 over 1, because if I do that, I'm going to have larger numbers rather than decimal numbers, which is a lot easier to proceed with the math. So my experiment is going to be experiment 2 over experiment 1, and I'm going to write my generic equation so you understand what we're doing. That's K, A to the X, B to the Y, and C to the Z. We're going to do the same thing for experiment 1, which is K, A to the X, B to the Y, and C to the Z. And now I'm going to plug the numbers in. Now I'm going to plug in for experiment 2, it's going to be K times 0.1000 molar to the X. For B, it's going to be 0.0500 molar to the Y. For C, it's going to be 0.0100 molar to the Z. That's experiment 2 data. And for experiment 1, it's going to be K times 0.0500 molar to the X. For B, it's going to be 0.0500 molar to the Y. And for Z, it's 0.0100 molar to the Z. This is equal to the rate. And the rate for experiment 2 is 1.25 times 10 to the negative 2 molar second to the negative first. For rate 1, it is 6.25 times 10 to the negative third molar second to the negative first. Now we need to simplify. So the K's are the same for the experiment, so the K's cancel out. The concentration to the X are going to reduce out to 2 to the X. The concentration for the Y's are going to cancel out because they are the same. The concentration for Z are going to cancel out because they are the same. And if I divide the right side, this is going to be 2. So 2 to the X equals 2, so that means X is equal to 1. Any number to the power of 1 is itself. So X must equal to 1. You're going to repeat the procedure to calculate for B, and you're going to calculate for C. So pause the video and try B and C on your own, and then check your answer. To solve for the order number for B, we're going to use experiment 2 and 3. So we're going to do experiment 3 over experiment 2 to get the larger number. So that's going to be K times the concentration of A, which is 0.1000 molar to the X, concentration of B, which is also 0.1000 molar to the Y, and then concentration of C, which is 0.0100 molar. And again, we chose experiment 2 and 3 because A and C will cancel out, so we are only left with one unknown, which is B. So for experiment 2, it's K. Concentration of A is 0.1000 molar to the X. So the concentration of B is 0.0500 molar to the Y, and the concentration of Z is 0.0100 molar to the Z. This is equal to the rate. The rate of 3 is 5.00 times 10 to the negative 2 molar second to the first. For 2, it is 1.25 times 10 to the negative 2 molar seconds to the first. Now I need to reduce. So the K's cancel out because they are the same. The concentration of A is going to cancel out because they're exactly the same. The concentration for C's are going to cancel out because they're the same. Now I'm going to reduce. So this is going to be 2 to the Y equals 2 is equal to 4. So Y must equal to 2 because 2 squared is equal to 4. We're going to repeat this procedure to solve for the reaction order for concentration of C. To solve for C, we want to use experiment 1 and 4, and we want to put the 4 on top so we deal with whole numbers. So for experiment 4, K is equal to 0.0500 molar to the X. For B, it's going to be 0.0500 molar to the Y, and then C is going to be 0.0200 molar to the Z. For experiment 1, it's still K. Concentration for A is 0.500 molar. For B, it is 0.0500 molar to the Y. And then for C, it's going to be 0.0100 molar to the Z. This is equal to the rate. Rate for 4 is 6.25 times 10 to the negative third meters second to the first. Same thing for reaction 1. They have the same rate. So now I'm going to simplify. So the K's are the same, so they're going to cancel out. The concentrations for A's are the same, so it's going to cancel out. The concentration for B is the same, that's going to cancel out. So 0.0200 divided by 0.01 is 2 to the z power. This is equal to 1. So that means z must equal to 0. Any number that has an exponent of 0 is equal to 1. So the general rate equation is rate is equal to k times a in bracket, and we solve for a up here. The order for a was 1. The order for b was 2. So order for a was 1. Order for b was 2. So my exponent is 2. My order for c is 0. When I write my rate equation, we do not include any reactant that is 0 order. This is just k brackets a to the first, b to the second. So this is my rate equation for this reaction. It is independent of the concentration of C. Now we need to solve for the rate constant, that is K. So I pick an experiment. It doesn't matter which one I pick, but I need to write it down. I'm going to use experiment 1. So using experiment 1, the rate for that is 6.25 times 10 to the negative third molar seconds to the first. And I'm going to plug in to my rate equation here. K, concentration of A, is going to be 0.0500 molar for experiment 1. And then B is going to be 0.0500 molar to the second, because it's a second order reaction. So now I'm going to rearrange and solve for my K. So K equals 50. Since it has 3 sig fig for exponents, we ignore the exponent and there's 3 in the front. There's a decimal and a significant digit in front, so these zeros are significant, so there's 3 here. And same goes here, so there's 3 and 3. I need 3 in my answer. Right now I have 1, so I need to put a decimal and a 0. So now I have 3 sig figs. To solve for the unit, if I look at my units here, on my left side I have molars over seconds. On the right side I have K, which is, we have K and we're looking for the units for K. We have molar from the A. We have molar squared from the B because it's a second order. So if I look at this, I could cancel out a molar on top here and a molar here. So if I rearrange my equation, K becomes 1 over molar squared seconds. Or I could rewrite this as molars to the negative second, seconds to the negative first. That is my unit for this. When I solve for K constant, you cannot memorize the units. The unit change. Its change is dependent on the order number of each of the reactants involved. So the overall order number is the addition of all the numbers together. So A has an order number of 1, B has an order number of 2, C has an order number of 0. So the overall order for here is 3. This is a third order. We write our equation as rate is equal to 50.0 molar to the second, second to the first, A in brackets to the first power, B in brackets to the second power, because that's the second order. Sometimes when you calculate for rate laws, the numbers are not whole numbers. You will sometimes get a decimal number. When that happens, you need to apply the log rules. If you look at this general equation, b to the x is equal to y can be rewritten as the following. Log base b y equals x. So if I have a problem, which is 45 to the x power is equal to 91,125. For most of you, you can't do that math in your head. So we're going to rewrite it. So log 45 becomes the base. The y, which is here, becomes the number in the parentheses, which is 91,125. This is equal to x, which was the exponent. In your calculator, the log works with base of 10. But here, the base is not 10. It is a base of 45. So we need to look at the next identity here, which state that log BA can be rewritten as log CA over log CB. And in this case, for this class, the log C will be a base of 10. This is what your calculator is based on. So what we do is we rewrite this equation using this identity. So that means X is going to equal to log, this is my A, 91,125 divided by log 45, which is the base. The way you punch this into the calculator, you punch in log 91,125, enter or answer, divided by log 45, answer. And if you do that correctly, you will get 3. Let's redo these orders using the log function. 2x equals to 2 looks exactly like this. So I'm going to rearrange it in the log format. The 2 is my b, my x is my exponent, equals to 2, which is my y. So I'm going to rewrite it in that format. So log, my b is my 2, my parentheses is my y, which is also a 2. This is equal to my x, which is my exponent. Since this is not a base of 10, I can't plug it into my calculator. So I need to look at my next identity and plug it in. And since it's base 10 that we're going to use in the calculator, I'm just going to write it as log rather than log of 10. So the format we have right now is log 2 parentheses 2. So that means I'm going to have log 2 over log 2. And you already know by looking at it, log 2 over log 2 is just 1. Or if you need to, you could plug this into the calculator, typing in log 2, enter, divided by log 2. You will still get 1. So let's do the one on the bottom here for y. If I rewrite my equation, this becomes log 2, parentheses with the 4 is equal to y, because that's the variable we're using here. And since it's not a base, we're going to use the second identity and rewrite it. Log of 4, because a is what was in the parentheses, and that was your 4, divided by log of 2. So you're going to plug in log 4, enter, divided by log 2, enter, and you should get 2. And let's do it for this one. So if I rewrite this, this is going to be log base 2 of 1, because that is 1 here. This is equal to the power, which is z here. Since this is not base 10, we're going to rewrite it. Log of 1 over log of 2, right? Plug this into the calculator. You should get 0. You could use either method, just do it correctly. Using squares and cubes are a lot easier than plugging into the calculator, resetting it up to solve for logs. Pause the video, try this problem on your own, and then check your answer. We're going to determine the reaction order of A, B, and then the overall. We're going to determine the rate constant and its units, and we're going to write the rate law. So the first thing you want to write is a generic equation. Rate is equal to K, which is the rate constant, times A to some power, B to some power Y. And we're going to solve for A first. It really doesn't matter which one you solve for, but it's better if you just go in order. You will make less error. So we're going to solve for A first. So in order to eliminate B, we need to make sure they are the same. And it's going to be reaction 1 and 2. Next, we're going to put the bigger numbers on top so we could deal with whole numbers rather than decimal numbers. So in this case, it's going to be reaction 2 divided by reaction 1. So we're going to have experiment 2 over experiment 1. So general equation is K. So for experiment 2, that's going to be 0.20 molar to the X and 0.10 molar for B to the Y over experiment 1, which is going to be K times 0.10 molar to the X, and for B is 0.10 molar to the Y. This is equal to the rates. This is 8.0 times 10 to the negative 4 molar times second to the first, divided by 2.0 times 10 to the negative 4 molar to the second negative first. Now I'm going to reduce. The K's are the same because it's the same reaction. And the B's are going to cancel out because they are the same concentration and same order. So 0.2 divided by 0.1 is 2 to the x. This is equal to 8 times 10 to the negative 4. You already know that those cancel out. So it's 8 divided by 2, which is 4. So then x is equal to 2. Or again, you could rewrite this. If you rewrite this, this is going to be log 2. 4 is equal to x. And since it's not base 10, we need to rewrite it. So this is going to be log of 4 divided by log of 2, which will also give you 2 if you plug it into the calculator correctly. Now we're going to solve for the order. For B, none of the A concentrations cancel out. 1 and 3, or I could use 2 and 3. I'm just going to use 1 and 3, so this is going to be experiment 3 over experiment 1, because I want to put the bigger one on top. That's going to be K. Concentration of A is 0.4 molar to the X. B is 0.20 molar to the Y over K. Experiment 1 is 0.10 molar to the X. And for Y is 0.10 molar to the Y. This is equal to the rates, which is 2.56 times 10 to the negative 2 molar second 1 for experiment 3, and for experiment 1 is 2.0 times 10 to the negative 4th molar second to the negative 1st. The K's cancel out. If you notice, the A does not cancel out, so I'm going to simplify it. So this is going to be 4 to the X, and then we know this is going to be 2 to the Y. This is equal to 128. We're going to simplify. I already know what X is. X is 2. We solved it above, so I'm going to plug that in. 4 to the second power, you already know this is 16. This is going to be times 2 to the Y equals to 128. So now I need to divide both sides by 16. This cancels out, so this becomes 2 to the Y is equal to 8. And so Y has to equal to 3. Working it with logs, this is going to be log 2, 8 is equal to Y. Again, this is a base of 2, so we need to rewrite it. So this is log 8 over log of 2. So if you plug it in, you should get 3. So in the calculator, if you push the log button itself, it is a base of 10. So my rate equation is K, concentration of A to the second order, concentration of B to the third order. To solve for K, we're going to choose an experiment. I'm going to choose experiment 1. So if I choose my experiment 1, my rate for experiment 1 is going to be 2.0 times 10 to the negative 4th molar seconds to the negative 1st is equal to K, which is what we're solving for. The concentration of A was 0.10 molar to the square, and for B it was 0.10 molar to the third. And we're going to solve for this K by dividing both sides by 0.1 squared and 0.1 cubed. You should get 20. So if I check my sig figs, there are 2 here. Exponents don't count. There are 2 here and 2 here because both of them have a decimal and a significant digit in front of 0. If I leave it as 20, there is 1, so I need to put a decimal. So now let's calculate the units. On the left side, the unit is molars per second. We're looking for the K units. On the right side, it's going to be molar squared because it's a molar and you have to square it. And then times molar cubed because you have to cube it. So I could simplify one of the molars. Then I need to divide by molars to the 4th power, because when we multiply molars, you must add exponents. And so that means I need to divide this side by molars to the 4th. So if I simplify this, K becomes 1 over m to the 4th second, or it could be m to the negative 4th second to the negative 1st. So if I rewrite my equation, this is rate is equal to K, which is 20 decimal molar to the -4 seconds to the -1st. This is A to the 2nd, B to the 3rd. The overall reaction order is going to be equal to 2 plus 3, so this is a 5th order. Pause the video, try this problem on your own, and then check your answer. This problem is pretty straightforward. We have a reaction 2A plus 3B yields C. Again, since this is a rate law, we ignore the products. We ignore the coefficient of the balance equation. It's a first order with A and B. So in this one, we don't even have to solve for it because they already gave you the order. So if I write my generic rate equation, that's going to be rate is equal to K. And since they're both first order, it's going to be times A times B. They give you the initial concentration, and we're going to look for the rate constant, which is K. So all we're doing is plugging in and solving. So this is 4.1 times 10 to the -4 molars per second, because they gave you the rate as this, equals to K. The concentration of A was given as 1.6 times 10 to the -2 molars. And B was 2.4 times 10 to the -3rd molars. So rearrange and solve for K. With correct sig figs, it's 11. Now we solve for units. So on the left side, we have molars per second. On the right side, we're solving for units for K. We have molars times a molar. One of them cancels out because they're both in the numerator, so I need to divide both sides by m. So when I do that, K equals to 1 over m times seconds, or m to the -1st, seconds to the -1st, either or. Pause the video, try this problem on your own, and then check your answer. The previous problem and this problem is straight out of your textbook. So to determine the rate law and rate constant, we're going to write the equation first, which is rate is equal to K times all the reactants. Since we don't know the order number, we're going to use different variables. I have to figure out which experiments to use. We want as much things to cancel out to simplify the math. So when I solve, I just go in order. So I'm going to use experiment 1 and 5 to solve for the first reactant. And I'm going to put experiment 5 on top to make it a larger number. So it's going to be experiment 5 over experiment 1. This is equal to K, which is 0.40 to the X times 0.050 molar to the Y times 0.050 molar to the Z. I'm going to repeat for experiment 1. This is equal to rate, so that's going to be 7.6 times 10 to the -5th molars per second over 5.7 times 10 to the -5th molars per second. Now I'm going to reduce as much as possible. Br2 cancels out, and so does the H plus. The K's will also cancel out. So if I simplify this, this becomes 1.33 to the X power equals to 1.33. So X is equal to 1. Or if you want to use the log, this will be log 1.33. 1.33 is equal to X. Since it's not base of 10, we have to rewrite it. So this is log of 1.33 over log of 1.33. If you notice, that's equal to 1. You can also plug it in. You'll still get the same answer. So now I'm going to solve for Y. And I'm going to use experiment 1 and 2. So I'm going to put the 2 on top because it will give me a larger number. So experiment 2 over experiment 1. Plugging it in, it's going to be K 0.30 molar to the X, 0.10 molar to the Y, 0.050 molar to the Z. And experiment 1 is K 0.30 molar to the X, 0.050 molar to the Y and 0.050 molar to the Z, and my rates are 5.7 times 10 to the negative fifth molar per second divided by 5.7 times 10 to the negative fifth molars per second. Now we reduce, the K's cancel out, CH3CO, CH3 cancels out, the H plus cancel out, so 0.1 divided by 0.05 is going to be 2 to the Y power, and on the right side it's going to equal to 1. So we know Y is equal to 0 because anything that has an exponent of 0 is equal to 1. Again, we could recheck this by rewriting it in the log format. So that's going to be log 2, 1 is equal to Y. Since it's not a base of 10, we're going to rewrite it as log of 1 over log of 2. And that equals to 0 if you plug it into the calculator. So next, I'm going to solve for H plus. So I'm going to use rate 4 and 5. And I'm going to put 4 on top because it's the larger. So that's also going to be K. This is 0.40 molar. X 0.050 molar to the Y. 0.20 molar to Z. And I'm going to fill it in for 5, reaction 5. The reaction rate for 4 was 3.1 times 10 to the negative 4, and for 5 was 7.6 times 10 to the negative fifth. Now I'm going to simplify, the K's cancel out, all my CH3CO, CH3 cancels out, all my Br2 cancels out, so this becomes 0.20 divided by 0.05, which is 4 to the Z. And if I divide my right side, I get 4. So we know Z is equal to 1. We could double check by rewriting the log format. So that's going to be log 4 is equal to Z. Rewrite it in the base of 10 is going to be log of 4 over log of 4, which is equal to 1. So my rate equation is equal to K CH3 COCH3, which was equal to order 1. BR2 was an order of 0. And then H plus was an order of 1. Anything that is a 0 order, you do not include. This is my equation for the reaction. Now I'm going to solve for the K constant as well as the units. So I'm going to be using experiment 1. And so this is going to be rate, which is 5.7 times 10 to the negative fifth molars per second equals to K, which is 0.30 molar times 0.050 molar, all to the order of 1. Rearranging, solving for K, you get 0.0038 with 2 sig figs because there's 2 here, there's 2 here, 2 here. The zeros that follow the significant digits are significant because there's a significant digit and a decimal in front. Let's solve for units. My units on the left side is molars per second. We're solving for the units for K. And we have a molar times a molar. One of the molars cancel out because they're both numerators. We're going to divide both sides by molar, so K becomes 1 over molar times second, which is molar to the first, second to the first. So that is my answer. So if I rewrite the equation, this becomes rate 0.0038 times H plus. Overall reaction order is going to be 1 plus 0 because the bromine was 0 plus 1, so it's a second order. So for rate laws, you need to first write a generic rate equation, and it only involves the reactants. No products are included. We also do not use the coefficient of the reaction. After you write your generic equation, you go to your table, figure out the experiments, or they'll simplify most of the variables. So what you want to do is you want to find reactions that have the same for every single reactant except for the reactant you are solving for, so you could cancel it out. After you do the ratio, simplify, solve for your exponent. Your exponent is the order for the reaction. Majority of the time, the exponents can be solved using your knowledge of squares and cubes. If you are stuck or you have a decimal number, make sure you use the log identities to solve them. In general, if you want to make the math easier, use the larger numbers for the numerator and the smaller numbers as the denominator. Once you calculate all the orders, the overall order is the addition of all the individual orders. If it's a 0th order, do not include it in the rate equation. After solving for a generic rate equation, solve for your rate constant by choosing an experiment and plugging the values in. You must always solve the units for the rate constant because it will change depending on what the order numbers are.